last time we took a look at the two-dimensional level curve summary or view of Lagrange multipliers. And then we'll take a look at both 2D and 3D aspects of this, just so we can get a clearer picture and get some more ideas. So here's one where we have our function that we're trying to maximize is z is equal to 3x squared plus 3y squared, so it looks like a paraboloid. And our constraint is x times y is equal to 1. So this looks similar to what we did last time, except the constraint and the function look like they're switched. So let's take a look at this problem and see how it'll work analytically, and then we'll take a look at graphs. So we have a function that we're trying to maximize. Remember, we're going to call that f, or it doesn't really matter what we call that. But we need our gradient of f. So let's just put gradient of f, and that's equal to the derivative with respect to x, and the first component, the derivative with respect to y in the second component. And then our g function, g is really a relation between x and y, but we're going to consider it as a function of x and y. And then the equals to 1 part makes it a level curve. But if we look at that with respect to x, it's going to be y and then x. So our Lagrange multiplier formula says that we're going to take the gradient of f, set that equal to some constant lambda times the gradient of g. This is going to give us, in this case, it's going to give us two equations, and then we're going to use the constraint as our third equation to find the three equations, three unknowns system. So gradient of f equal to lambda times gradient of g, so this is going to be 6x equals lambda times y. 6y equals lambda times x. So we have two equations, and we have the three unknowns x, y, and lambda. So our third equation is x times y is equal to 1. This is a system of equations that we're going to solve for. Okay, so how are we going to solve for this? Well, I don't know. How should we solve for this? We can go around in circles in these things, so you just have to be careful about, when you're trying to solve for this. There's a lot of different approaches. So let's see. One approach might be if we solve for lambda up here, lambda is equal to 6x over y. Now, if I divide by y, I have to make sure that it's not equal to 0. So I'm going to make a special note of that, that might be a special case. And then over here, lambda is equal to 6y over x, again making a special note where I divided by some variable. So 6x over y must equal to 6y over x. And then that would be what? 6x squared is equal to 6y squared. And then what? Suppose we can replace it with one of these variables. say if we replace y with 1 over x, again, provided that x is not equal to 0, and put that in here, you're going to get 6x squared is equal to 1 over x squared. Oh yeah, we can take the 6 out. That might be helpful. It looks like we can x to the 4th equals 1. So it looks like our x could possibly be equal to plus or minus 1. Does that look okay? There are many other ways to do this. So this is just one way. And I need a point. So I need my y value. And this is the relationship between x and y. So when x is equal to 1, y is also going to equal to 1. And when x is equal to negative 1, y is going to have to be equal to negative 1. They have to have the same sign because the output is 1. Now the question is, in this system, can x or y be ever equal to 0? Because we assume that it's not equal to 0 here. Can it ever equal to 0?
Yeah.
So this thing, our special restriction here, when we set x or y cannot equal to 0 if I do it this way, means that I have to consider later what if x was actually equal to 0 or what if y was actually equal to 0. And so we have to ask yourselves, is that ever going to happen? And the answer in this particular problem is no, because you have one of your important equations as your constraint that says x times y is equal to 1. So if x or y were equal to 0, then this isn't going to work anymore. So we can make a note here to say x cannot equal to 0 and y cannot equal to 0. So we don't have to revisit that anymore. And I think we found the points that we're looking for. Now, if we look at the question carefully, which we didn't do last time, I didn't do last time, here they're looking for the actual values. So I have points. To get the actual values, I need to plug those points in. So let's plug those points in. What if I get 1, 1 here and put that into the function f? So f of 1, 1, what's going to happen there? Well, I'm going to put 1 in 6. One in for x, 1 in for y, into my original function, 3x squared plus 3y squared. And then if I put negative 1 in here, I'm going to get 6 also. Same maximum and minimum value, you think? What do you guys think? What? Does it make sense? I don't know. So what we could do is we can try another point here to put in here and try to see whether it's going to be bigger than 6 or less than 6. So 6 is either going to be a maximum or a minimum. I don't think it could be both. So if we put another point, like what if x was equal to maybe a half? I was going to say 0, but that's not going to work. And so y is going to have to equal a 2. Is that right? 1/2 and 2. So f of 1/2 comma 2. So f is going to be, what is this going to be? 3/4 plus 4 plus 12. Wait, what? And what's this equal to? It's what? 51/4. I guess, is it less than 6 or bigger than 6? This is bigger than 6. So it looks like if we put points on this, from this line into the function, we're going to get values that are going to be bigger than 6. So when we get values that are bigger than 6, that's going to make 6 your minimum value. Minimum. And then we can assume that this thing just kind of goes up forever. And so it looks like we're not going to have a maximum value. Does that make sense? Mm-hmm. Should we test our answer? Yeah, that's right. I trust this. Okay. I wish I could just trust your test answers. Boy, that would make grading so much easier. 100%. Wow, awesome. In spirit, you guys got all 100%. So here is the two functions from a what do you call it? From a level curve perspective. And there's that one special level curve that is not shown here because this is just a contour plot curve. And when you assign contour plots to a lot of graphing programs and you don't specify which contour, it's just going to draw a bunch of randomly selected contours. So there is this one circle that's going to be, kissing our graph x plus y is equal to 1. So that's going to be a contour of this function. So the question for you is, what contour is that? By which contour this is that if I take that function f and I set this equal to some constant, which constant is it? 6. How did you get 6? That's the y value, right? So if we do that, we get that last circle that's going to be kissing those graphs, or that would have gradients that are collinear. Okay? So this is the view. This is one view of our contour curves. It's also interesting to look at this from a three-dimensional perspective. If I were to graph z is equal to 3x squared plus 3y squared, what is that going to look like? Is there a name for that? Yes, there is a name for it. What's the name of that? It's a paraboloid. Okay? If I were to graph x times y is equal to 1, what do you think I'm going to get? No. No? Okay, let's look at this carefully. This is x times y is equal to 1. Now, there's an observation that I can make here. I don't see a z value. I don't see the z variable. So what do you think it's going to look like? Let me show you that x times y is equal to 1 looks like these hyperbolas off to the first and third quadrants. So now, what do you think the surface is going to look like? Just like that as a what? You think it'll just stay on the plane? It's on all C values. What is this called again when one of the variables is missing? Cylinder. Remember cylinders? Yeah. Cylinders are, you know the cylinder that we learned when we were in kindergarten or whatever. It's that can, right? That's a cylinder. Really what that is a circle that's being swept up and down the z-axis. Right? So that's what a cylinder is. But you can have y is equal to x squared as a parabola if you look at it down on the xy plane. But if you put it in 3 dimensions, you'll have that parabola that's being swept up and down the z-axis. So you can imagine this curve being swept up the z-axis, and that's going to be your surface. X times y is equal to 1. All right, so let's take a look at that. I adjusted the settings a little bit so we can kind of see what's going on. And maybe I need to change the color for this one. So this is what's happening in 3 dimensions. It's still hard to see. And really what we want out of this is, boy, I don't know how I'm going to draw this. Can you guys see this? Should I change this to yellow maybe? Gray? What? Made it a little worse. I think I want this lighter, and I want this one darker slightly. Slightly. Okay. Well, I could see it nice and clear from my point of view. I know the screen sucks, but let's take a look at. I kind of want a screenshot of these pictures too. So let me take a screenshot of the level curves that we were looking at, and make a note to ourselves that we actually got a level curve of f of x y is equal to 6. So we have, oh, never mind. I was going to retrace it, but let's just say x, y is equal to 1. Does that curve, and this particular curve over here is a level curve f of x, y equals 6. All right, so that's our 2-dimensional picture. Let's take a look at our 3-dimensional picture and see what we can get out of this. And what I'll do is I'll annotate this with a color, maybe red. I can't see.
Oh, I thought it was just fine.
It was. All right. All right, let me see if I can add on to this thing. And for this, I think I need to go. I need to go to parametric equations. T1 minus T and 3 t squared plus 3 times 1 over t squared. If you guys understand what I did, then you're in great shape. And if not, don't worry about it. Okay, what I was trying to draw here is that if I take those curves away, oh, I need both of them. Damn it. Can I do plus and minus? No. No, they're not even connected. They're supposed to be connected. All right, well, so on this curve, we have the intersection of let me see if I can just draw it. All right, you have a paraboloid, and you have these things on the floor that are the hyperboloids that go and get swept up, right? They get swept up. And so what happens is that they intersect the paraboloid somewhere. They intersect the paraboloid. So that place where they intersect the paraboloid, if we looked at it from the last section when we're taking a look at the maximums, absolute max and mins, we're looking at the boundary and the inside. Here, with Lagrange multipliers, we're not looking at the inside, we're only looking at the boundary. The constraint is really just the boundary, so we're really focused on the boundary. So that boundary is the intersection between those two surfaces, and you can see here that the paraboloid keeps going up forever, and so these intersections will keep going up forever. That's why in our problem here we didn't have a maximum. And we do have a minimum value, and that's the lowest point for the intersection between these two surfaces, and that is our minimum value at 6. So if you can see this graph, and if you drew a plane at level 6, you'll see that these two graphs will intersect here. And then if you go further out, you can see that there's more level curves for the f function, but then it's not gonna be close to the constraint. Okay? So you see the picture? If you can visualize it in 3D, that's great. What is important is the 2D representation, the level curves, where the graphs are going to be collinear. The perpendiculars, the gradients are going to be collinear. They have the same tangent, so they're collinear. The gradients are collinear, and we're working on the idea that the gradients are perpendicular to the level curves. What? Let's draw the gradient. Let's draw the gradient. So we're looking at this picture for the gradient because our functions are two-dimensional. Now, for the gradient of the circle here, I have two possible choices. One of them points in, the other one points out. Which way is my gradient going? Because
as we are increasing the level of curvature.
So the other picture, if you can view this, you can look at the three-dimensional picture, which is this surface, a paraboloid, and the way to increase and go higher would be to go outward, right? If you imagine you're on this bowl, you're a little ant on this bowl, right? If your direction is an outward direction away from the center, you're going to go up the bowl. If you're on this bowl and you go in towards the center, then you're going to go down. So remember that the gradient is a maximum increase, so you want to go up. So the gradient for this example goes outward. Okay, and so since this is a level curve, we can just guess what might happen here, or we can actually take the gradient that we found, x, y, positive x, positive y, positive x. That's the gradient. So at the point 1, 1, it looks like it's going to be 1, 1. So the gradient here for this curve is also going in the same direction as the gradient for the other curve. They might not be the same length, and they probably are not the same length, because I think the gradient for f is longer, but that's the point is that they're collinear. Okay? Oh, one more thing that we didn't do, I don't know if you noticed, we didn't solve for lambda here, right? Again, lambda doesn't matter. We really care about the x and y values. So if you have to solve for lambda, then solve for it to help you solve for x and y. But in this case, we didn't solve for lambda, and it doesn't matter, so we just leave it at that. It doesn't give us any valuable, pertinent information, yeah, for the problem. All right, let's do another Lagrange multiplier problem. This time, let's go take a look at a three-dimensional example. By 3D example, I mean an example where you have a function of 3 dimensions. Oh, that one looks hard. Let's do this one. That one looks hard too. They're all hard.
Yeah.
Labor and tricky. All right, so my function is going to be x, y, z, x times y times z. And then my constraint is x squared plus 2y squared plus 3z squared is equal to 24. Now, if we just remember the formula without any variables, then this will apply to any dimension we want. So the difference between this problem and the ones that we did is that we're going to get 4 unknowns. We're going to get 3 equations out of this gradient, and plus the constraint, we're eventually going to get 4 equations and 4 unknowns. All right? So let's get our gradients. With respect to x is going to be yz, xz, xy. Gradient of g, if we call this our g function, is going to be 2x, 4y, 6z. And then we write our equations. Yz is equal to lambda times 2x. Xz is equal to lambda times 4y. And xy is equal to lambda times 6z. Okay. Oh, so I have three equations. I have x, y, and z, and lambda, four unknowns. So to get my fourth equation, I just use my constraint. So x squared plus 2y squared plus 3z squared is equal to 24. And you don't have to write it the way I'm doing here, because if you just remember that this is a constraint, I just rewrote the constraint over again. But I think it might be good practice just to keep the equations together that you're working with instead of trying to remember, oh, what's my last equation? Okay, so there's a little trick to this. I don't know if this trick will work. We'll see what happens. I see an x, y, z potential over here. Potential. I can make the left-hand sides of these three equations look the same. If I just multiply by select variable. What? So I think maybe what I'll do is I'll multiply the first one times x, and so the left-hand side will look like x, y, z. I'll multiply the second one by y, and then the third one by z, and so all my left-hand sides would be x, y, z's. So x, y, z is equal to lambda times 2x squared. X, y, z is equal to lambda times 2 for y squared. And x, y, z is equal to lambda times 6z squared. And it looks like I can also divide by 2 lambda. Lambda, by the way, can never equal to 0, so that's safe to do that. And so let's divide by 2 lambda. X, y, z divided by 2 lambda is equal to, that's just going to be x squared. And if I do that to the second one, it's going to be 2y squared. And if I do that to the third one, it's going to be 3z squared. And these are all equal to the same thing, so I can set them all equal to each other, right?
Yeah.
So I got x squared is equal to 2y squared is equal to 3z squared. Hey, look, those are exactly the terms over here. So why don't we just make them all x squared? So this will help me find my x. And if I can divide, is it 8? Then I can solve for x. And once I know x, I know that x squared is equal to 2y squared. And so I can solve for y. And then I can do the same thing for z. Okay? Now, it looks like I have possibilities of pluses and minuses and stuff like that. So I would have a combination of, oh, let's do some probability and statistics here. How many points am I looking at? 6? Okay, so there's 6 points. I don't know. Plus, plus, minus, minus, and then et cetera, et cetera. Come on, Cameron. What is it?
Wait, don't you do like
8.
you do 3 times 2 times. It's like stacked. Yeah, it's 6.
It's 8. So it's 2 times 2 times 2. So there's 8 possibilities. It's okay, nobody listens to the videos anyways.
But you can't hear the...
Yeah, you can't hear the... Unless I say Mimi said that there was... All right, so we have 8 possibilities. That's a lot to check, but the only difference is the pluses and minuses. So I think if we just consider this thing and then put a combination of pluses and minuses would be good. So remember that the function we're trying to maximize is f. And then f is equal to x times y times z. And so if I just switch the signs, 2 negatives, 3 positives, and all that, the combination, it's just going to be either a plus or a minus. So let's just consider the positive ones. That's square root of 8 times 2 times square root of 8 over 3. So 16, I guess that's 8 times 2 is 16 over square root of 3. And if they were all positive or all negative, then this would be a positive. And if 2 of them are negative or 2 of them are positive, whatever the combinations are, they're either pluses or minuses, right? So I think in either case we'll have either the maximum would be positive 16 over root 3, and then the minimum would be negative 16 over root 3. Okay? Any questions? So, the idea of the Lagrange multipliers is just the gradient times the gradient of the function you're trying to maximize times the gradient of the constraint. Now, the lambda, I always put the lambda next to the constraint, but really lambda cannot equal to 0. If it's equal to 0, then this whole thing doesn't work anyways. So technically, I could have put the lambda over to the other side, and it wouldn't make a difference. I mean, from one point of view, I can just call it 1 over lambda, or I can just have lambda on the other side. It's the same thing. So it doesn't really matter where your lambda goes. And again, in this particular problem, we didn't solve for lambda. It doesn't really matter what lambda is. And what you really want to look for are the x, y's, and z's, or x and y's. And in this case, we had to use, this was a little tricky, I thought. This is not something that I would have thought of unless I've seen this a bunch of times already. And so when you're just looking for these things, there are some tricks that you could use aside from the usual brute force method of just solving for one variable. Especially when you're dealing with 4 variables and 4 unknowns like this, and it's not linear, it's not going to be an easy task. Okay, so try to pick up a bunch of these little tricks as you go along. And if you're really, really stuck on a problem when you're doing your homework, just Wolfram Alpha it. Just say you have a bunch of equations that you're trying to solve for. Help me solve for this. Actually, let me show you how to use Wolfram Alpha for that. Uh-oh. No internet connection?
I was about to say. The internet at school once it starts working.
All right, well, no internet connection. So that must be a sign. Any questions? Okay, so that's it. Graph it? Should we graph it? Let's take a look at graph. Too late, on its way out. What's the constraint look like in terms of what the graph of this should be? What do you think this is? Ellipsoid? So we have a graph of an ellipsoid, and our second graph, we actually, because this is a three-dimensional problem, we actually need to look at it as a level curve already, a level surface. So x times y times z is equal to, and our level surface is 16 over the square root of 3. It's kind of kissing. It's actually more pieces, so if we get more pieces like that, you can see, you can kind of see 6 places that it could have been, or 6 or 8 places. It's supposed to be 8, right? Oh, there's only 4. Yeah, you guys work it out. Have a good spring break.